I'm currently in the process of moving my CPU build from breadboards to PCBs on a proper backplane. And in the previous episodes, we've already built the PCB for the arithmetic logic unit, the program memory, and a long time ago also for the program counter. Today, I think it's time to take these three PCBs and move them onto a backplane. We've already sketched out how things should look like in the end. We have the ALU, the program counter, and the program memory, all sitting on a backplane which we can connect to the register file backplane on the left. And we'll have a bunch more connectors at the bottom to access the pipeline specific signals. So without further ado, let's go and draw up some schematics for this. We first need to create schematic symbols and footprints for the PCBs that we're going to place on the backplane. Let's start simple with the program memory. Then we need the symbol and the footprint for the ALU. And last but not least, the program counter also needs a symbol and footprint. Alright, with the symbols and footprints all done, it's time to actually create the schematic for the backplane and place these modules there. To get started, let me copy the left and right connection headers from the register backplane. Let me also reuse the same clock buffers. And then let's add the modules we've just created. Before establishing all the connections among the modules, let me first create the PCB layout and roughly arrange things. Let's start wiring up the program memory. First, the address inputs will go to a header. The clock will just hook up to the clock of the backplane. The output enable will also go to a header. And the data output will also go to a header. And let me maybe add another data header, just so we have enough of them. Now, on the breadboards, we've been interpreting the data that comes out of the program memory as instruction bits. And we've used various parts of the 16 instruction bits to drive different parts of the CPU. Some have been hooked up to the immediate, some to the register addresses, etc. And I think it would be a good idea to make some of these connections here on the backplane directly. So let me create a separate instruction signal, which is 16 bits, that we are going to connect to various pieces of what comes out of the program memory. And I'm going to use a 74HC 541 buffer that we can enable or disable to drive the data coming out of the program memory onto the instruction bits. Because I suspect later on when we do handshaking in the pipeline and we make sure that the pipeline is stallable, we might not want to always take the instruction data directly from a ROM, but we might want to have a separate instruction register where we keep the instruction around in case the memory is busy. So these buffers by default will drive the data coming out of the program memory onto the instruction bits. Let me also add a pull-down resistor to the enable signal such that these buffers are enabled by default and drive the instruction coming out of the program ROM onto the instruction bits headers. And then let me connect the instruction bits to the corresponding control signals like we did on the breadboards. And I'm going to use these jumper pads which have a connection by default between them, but it's a very thin piece of copper that you can cut easily, just in case we at some point decide that we don't want to make these connections anymore. Then let's move on to the program counter. Most of the control signals of the program counter we'll just put on a header such that we can connect to them from the instruction decoder that we're going to build. The absolute jump address input we have connected to the read data port 2 and 3 of the register file. So let's do the same here on the backplane. The relative base address we've left unconnected, and I don't see any use for it here in the backplane either. The relative jump offset we have taken from read data port 2. We haven't used the step address for anything on the breadboard, but I think once we're going to do function calls, it would be good to have this available. So let me route that to a header such that we can connect to it. And the program count output we'll use for quite a few things, but let me put it on a header first. On the breadboards, we've directly connected this program count to the address input of the program memory. But later on, when we add RAM, we'll want to access the program memory and also the RAM through the load store unit, which is going to drive its own address. So I don't think we want to always drive the program counter onto the address bus. We want to do that through a bunch of buffer chips, which we can enable or disable. And the control signals that turn the buffers on or off are going to be our program counter output enable. And let me keep both of those and bring them out onto a header. And then by default, we'll just tie them low such that they're active. And then later, once we have RAM and the load store unit wants to access memory, the load store unit can just disable this program counter output enable and take control of the bus. Let me also use pull up and pull down resistors for some of the other control signals to set them to a sane default value. And finally, let's wire up the ALU. The left-hand side input we've connected to the read data bus 1, and the right-hand side we've connected to the read data bus 2. The result goes directly onto the write data bus. The flags input comes from the flags read data bus, and the flags output goes to the flags write data bus. And all the other inputs will just connect to a header such that we can connect them to the future instruction decoder. And I think one thing we could do is we could drive a default value onto the LED enable of the ALU. We could, for example, AND the flags and the result output enable and use that as an LED enable. Now let me add a few headers for the control signals. We'll also need a few decoupling capacitors for the chips. And then let's go arrange this on the PCB layout. I think I'm going to use a 4-layer PCB again, just for the reliable power distribution. And then let me roughly arrange the components. Then let me get some of the routing out of the way here. And then finally, let me distribute the clock and reset signals. Okay, looks like these are all the wires that we need. Let me go clean up the silkscreen a bit. Alright, that looks like a pretty cool backplane for the pipeline. Let me order this up, and when I get it back from the manufacturer in just a bit, let's assemble it. I've just gotten the PCB and stencil back in the mail. Let me clean one up and apply some solder paste to it. And then let's add some components. Let me start with the smallest. We have 7 100 nanofarad capacitors. Then we have 7 100 kilo ohm resistors. Then we have a single 74HC1G08 chip and two 74HC1G34 chips. And finally, we have 4 74HC541 chips. Alright, that's it. Let me fire up the hot air gun and solder this up. That looks pretty good. Let me give this a quick cleanup off camera, and then we'll add all the headers. Then there are a whole bunch of headers for the PCBs. Alright, this looks pretty good. Let me give this a quick cleanup off camera and then let's see if it works. Okay, so let's see if we can power this up and make it do something interesting. First, let me just connect the clock generator to see if anything catches fire. Alright, nothing catches fire, and the clock generator apparently has power and it's currently in reset. And when I toggle the clock, I can step it out of reset. Let me add the program counter to the backplane. This still powers up with no problem. The program counter is enabled by default by the backplane, so that seems to be working. Let me hit run on the clock and let's see what happens. Pretty cool, the clock is ticking and the program counter is counting up. By default, the step size is configured to be 2 bytes, and the program counter mode is set to 0 by default, which is just doing single stepping mode. And so whenever the clock ticks, the program counter counts up by 2. I can then deactivate the program counter enable line of the backplane, which makes the enable go low, and nothing happens when you hit the clock. Similarly, I can set the step size to 1 byte, which makes the program counter count by single byte increments. Or I can set the step size to 4 bytes, which makes the program counter count by 4 byte increments. Pretty sweet. And since we're generating program addresses, let me add the program memory such that we have something to read out. Let me step it out of reset. And that looks pretty good. We're at address 0. And indeed, in our program, this is still the conditional move testing program, In our program, address 0 is a load immediate followed by a bunch of moves. Followed by another load immediate, and then followed by a flag swap operation. So that seems to be working. We can step through the program and the program ROM is producing the actual instructions at those addresses. Let me try to get those load immediates and moves back up and running. For this, we'll need the register file backplane. And I've also created this simple connector piece here, which we can use to connect the two backplanes. Okay, so we're back at this load immediate instruction. First up, we'll want to constantly enable the read data ports. And then we have the write enable of the registers connected to instruction bit number 7. And this is where this backplane comes in handy. We have the instruction that the program ROM produces nicely brought out to a pin header at the bottom. Furthermore, we'll want to connect the immediate output enable back to instruction bit number 3. This now makes the immediate output enable LED on the register file backplane light up. And similarly, we want to connect the move output enable back up to instruction bit 2. And since instruction bit 2 is a 0, this is an active low signal, the move output enable on the register file backplane turns on. And the immediate mode we'll set to 0 for now to always load 8-bit immediates. When I hit the clock, the load immediate executes, but register R0 was already at 0. So now let me step through the move instructions, which are going to clear the register file. Pretty cool, that seems to be working. And now we're loading a 1001 into register R0, which also works. And now we're back at this flag swap operation that we had before. So let's add the ALU. And we've been using this breadboard with an OR gate and an inverter to control some of the ALU control signals. Let me power this back up. Let me hook up the result output enable of the ALU first. We've been using the inverter to enable the ALU whenever we're not doing a move. So let me do that again here. Let me step forward to that flag swap operation again. Pretty sweet. The move buffer is disabled and in turn the ALU's result is now enabled. And then furthermore, we've been using the OR gate here to control when the flags output of the ALU is enabled. We've been using instruction bit 11 ORed with the ALU enable. This basically allowed us to enable the flags whenever the ALU is enabled and we're not doing a conditional move. So whenever bit 11 of the instruction is not set. Let me also use this flags output enable of the ALU as a flags write enable for the flags register, such that whenever the ALU produces new flags, they get stored in the flags register. So this enables the flags output of the ALU, and it enables writing of the flags register. But the ALU isn't executing the correct instruction yet. We have to hook up the opcode for that. The lower 4 bits of the opcode were in the topmost bits of the instruction. And instruction bit 11, which we've used to determine the flags output enable, is also used as ALU operation bit 4. And here we go, the ALU now performs the correct operation. Logic operation 1111 is the flag swap operation, and correspondingly you can see that the flag swap LED here is turned on. And so when I hit the clock, we expect the 1001, which is currently in register R0, to be copied into the flags register down here. Which is exactly what happens, and the contents of the flags register, which were all 0, are now in register R0. Next up is another load immediate. We're loading 1 into register R0, which works. And then we perform a conditional move from register R0 into register R1. And since we're doing a conditional move, the flags output enable of the ALU has been turned off such that the move doesn't affect the flags that are currently stored in the flags register. And since the carry flag is set, when I hit the clock, you can see that the 1 from register R0 got copied into register R1. That seems to be working pretty nicely. I think the only thing that's missing right now are jump instructions, which aren't properly hooked up yet. Let me fast forward to the first jump instruction in the program. Here we go. This is a jump relative with register, and you can see the lowest bit in the instruction is set, which indicates that this is a relative jump. But the program counter's mode selection is still at 0, and this is because we haven't hooked up the select signal yet, so it defaults to just stepping mode. So let me connect the lowest 2 instruction bits to the program counter mode select input, which is what we've been doing on the breadboard. Alright, and this now properly selects program counter mode 1 when we're doing a relative jump. And so when I hit the clock, we won't see the program counter increment by 2 bytes, but actually go backwards a bit because we're adding a negative number. Perfect, that worked like a charm. At the end of this program, we're still computing the largest 16-bit Fibonacci number. So let me hit run on the clock and let's see what happens. Pretty cool, this still produces the number 46,368, which indeed is the largest 16-bit Fibonacci number. So it looks like we've successfully moved a whole bunch of breadboards onto these 2 backplanes, and the CPU still works exactly like it used to. This thing has turned out really compact. If you remember, the ALU alone used to be a stack of 6 breadboards here on the left. The program counter used to be 2 breadboards stacked. The register file used to take up quite a bit of space, and the program ROM was also split out across 1 or 2 breadboards. And the wiring situation has definitely improved. Most of the interesting signals go through this middle connection here, and so all we had to do here at the bottom of the pipeline backplane is hook up a few control signals, which we'll still want to change as the CPU evolves. So I think we're now in an excellent spot to go in and come up with an instruction decoding scheme. Because we have all the control signals available here, we can build up an instruction decoder on the side or below the pipeline backplane here and figure out how exactly we want to translate the instruction bits into the control signals that the CPU needs. And if you remember, when we added the ALU in some of these operations, we actually had an add with immediate instruction, which we had to get rid of because it collided in the opcode space with some other instructions. But now with some proper instruction decoding, we can bring these instructions back and look at other instructions that might be interesting, such as AND with immediate, OR with immediate, XOR with immediate, and a few others. And then once we have a basic instruction decoding and we have some more information available, which registers we're actually reading and writing, we can start to look into the first out-of-order features of this processor. I can't wait for that to finally happen. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.